Okay, objective 5 for unit 4. We are doing limits as x approaches infinity. In other words, as x goes forever to the left or as x goes forever to the right. We want to understand graphically what's going on. We want to understand what's going on also analytically. Might do a little bit of numerical as well, but here we go. Now graphically, essentially you're looking at the graph and you're trying to see if the graph levels off to a certain elevation as you're going to the left and the right forever. So for example, here on this first graph, the graph of y equals f of x, as we're going out to the right forever, isn't it seeming to level off at about elevation 2? And as I go out to the left forever, isn't it also leveling off at about elevation 2? And so therefore, the limit as x approaches infinity for f of x is 2. Okay, if we look at our next graph, y equals g of x, well, as I go to the right, it seems to be leveling off at elevation -3. As I go to the left forever, it seems to be leveling off at elevation -3. Therefore, the limit as x goes to infinity for g of x is -3. Okay, the graph of h of x, as I go to the right forever, it seems to be leveling off at elevation 0. As I go to the left forever, it seems to be leveling off at elevation 0. Therefore, the limit as x goes to infinity for h of x is 0. Finally, the graph of p of x, as I go to the right forever, it doesn't seem to be leveling off. In fact, it kind of seems to be doing almost like a certain slope there, but seems to be going down forever as I go to the right. As I go to the left, it seems to be going up forever as I go to the left. So this one is not leveling out, and so therefore the limit as x goes to infinity does not exist. Now, for the most part, we will be doing graphs where it levels out to the same elevation as we go to the left and the right forever. And that's mostly what we will be dealing with. That's not to say that that always happens in every function. It is possible to have a function where it levels off at one elevation going to the left and it levels off to a different elevation as it goes to the right. If that is the case, then you'll just have to do the limit as x goes to negative infinity separate from the limit as x goes to positive infinity. But in general, if we're not really differentiating, it's just, in general, it's just limit as x goes to infinity. Okay, we have 4 review questions here right now based on the graph, so why don't you go ahead and do those real quickly. Pay attention to which graph you're supposed to be looking at, okay? Okay, so if we check those answers here real quick. Number 5, we're doing the limit as g approaches 1, and it's about 3.5, negative 3.5. And if we check the limit as h for h of x as x approaches negative 1, pretty close to negative 2. If you said negative 1.9, something like that, that would be okay as well, but about negative 2. Limit as x approaches 2 for h of x. Okay, it's about 0.5. And finally, limit as x approaches 0 for f of x, and you know that's about 1.5. Okay, so that was just review right there. Okay, let's move on to the analytical. There is one main rule for limits as x approaches infinity. So the limit as x approaches infinity, and it really doesn't matter whether it's positive infinity or negative infinity, of a constant over x to positive powers is 0. Okay, that's the main rule. Okay, so number 9, we're evaluating, we're doing this by analytical methods. Okay, so, and at this point you're going, well, I don't have anything quite like this. Okay, well, what's the highest power of x in either the numerator or the denominator? X to the first. So I'm going to multiply top and bottom by 1 over x to the first. So if I do that, we get the limit as x goes to infinity. You keep writing limit until you actually take the limit. And I have 3 plus 1 over x all over 5 over x minus 2. Now, how did that help us? Well, we're still taking the limit as x goes to infinity, and here is a constant over x to the positive first power. And so that is going to 0. Here is a constant over x to a positive power. And so that is going to 0. And we're left with 3 plus 0 over 0 minus 2, which is negative 3/2. And so there's the limit as x goes to infinity. Okay, let's try that again. So number 10, what's the highest power of x, either in the top or the bottom? Well, the highest power of x is the x to the third. So I'm going to multiply top and bottom by 1 over x to the third. And so that gets me the limit as x goes to infinity. I would get 2 minus 5 over x plus 1 over x to the third all over 7 plus 4 over x squared minus 3 over x cubed. Okay, so all the constants over positive powers of x, those go to zeros. And we're left with 2/7. Next one. Highest power of x in either the numerator or the denominator is 2. So I'm going to multiply top and bottom by 1 over x squared. And if I do that, I get the limit as x approaches infinity of 6 minus 5 over x plus 2 over x squared, all over 27 over x squared minus 3, which is 6 over negative 3, and always reduce, negative 2. Okay, let's move over to problem number 12. Problem number 12, same directions. What is the highest power of x there in either the numerator or the denominator? X squared. So I'm going to multiply top and bottom by 1 over x squared. And we get the limit as x goes to infinity. I get 4 over x plus 3 over x squared, all over 9 over x squared minus 1. That's 0 over negative 1, which is 0. Next one. Highest power of x in either the numerator or denominator is x to the third. So I'm going to multiply top and bottom by 1 over x to the third. So we get the limit as x goes to infinity of 5 minus 2 over x squared plus 7 over x cubed, all over 3 over x plus 1 over x squared minus 1 over x cubed. Okay, now I'm noticing that my denominator is going to be 0, so I'm not going to write equals. I'm going to do an arrow here. So my denominator is 0 and my numerator is 5, because that's an undefined value. So don't say equals when it's undefined. And so since it's an undefined value, the limit as x goes to infinity does not exist here. In other words, the function was not leveling off at some elevation as it went to the left and the right. Okay, number 14. Now, by the way, there are some patterns going on here, and I hope that you're trying to notice some patterns, because we are going to take some shortcuts. We're not quite there yet, but we are going to be doing some shortcuts with these. Okay, so highest power of x, top or bottom, is x to the 5th. So if I multiply top and bottom by 1 over x to the 5th, we get the limit as x approaches infinity, and I have 4 over x to the 3rd minus 2 over x to the 4th plus 13 over x to the 5th, all over 1 plus 3 over x to the 3rd minus 4 over x to the 5th. So that is 0 over 1, and by the way, 0 in the numerator, remember that's not a problem. 0 over 1 is 0. Now, I said that we're going to be doing some shortcuts. Hopefully you've been kind of trying to pay attention and notice some patterns here. Anybody just kind of look at the next one, maybe have an idea of what you think the limit's going to be? What do we notice? I noticed that the highest power of x is the same in the top and the bottom. The degree in the numerator and the degree in the denominator is the same. Okay, so if I'm multiplying top and bottom by that, so 1 over x squared, we do get the limit as x goes to infinity of 4 plus 5 over x squared, all over 7 over x squared minus 2. And that is 4 over negative 2, which is negative 2. Is it what you were maybe thinking? We're going to be trying to write down the pattern here in just a minute. Okay, number 16. What's the highest power of x? Well, the highest power of x is down in the denominator. It's x to the fourth. Think about, have we encountered any others where the highest power of x was in the denominator? Yeah, go back and look at those. See if you can anticipate what the limit as x goes to infinity is for this one. So multiplying top and bottom by 1 over x to the fourth. And I would get the limit as x goes to infinity. I have 5 over x minus 2 over x to the third plus 7 over x to the fourth, all over 3 plus 1 over x squared minus 1 over x to the fourth, which is 0 over 3, which is 0. Is that what you were thinking? Hopefully that's what you were thinking. Okay, so what are the patterns that we are noticing? Because there are 3 main things that we want to notice here. For example, the last problem we just did, the highest power of x was in the denominator. The degree in the denominator was greater than the degree in the numerator. And so I might refer to that one as being bottom heavy. So, and by the way, this only works when we're doing the limits as x goes to infinity. You do not apply these to the other type of limits that we did in 3.4, the limits as x approaches some constant. But for limits as x goes to infinity, so the degree in the denominator is greater than the degree in the numerator. So if that's the case, the limit as x goes to infinity for that function is 0 every single time. Okay. Another one of the situations we had is when it's top heavy. In other words, where the degree in the numerator is greater than the degree in the denominator. And so if we have that situation, that one will be does not exist every single time. Okay, that leaves one other situation that was happening more than either of those last two. And so the other situation is where the degree in the numerator and the degree in the denominator is the same. So it's equally weighted. Okay, and that's the limit as x goes to infinity for ax to the n plus stuff over bx to the n plus stuff. And so equally weighted, the degree is the same top and bottom. And so what was happening there? Well, you take the leading coefficient and you make a fraction, reduce it if it reduces. Now, we really don't want to be showing a bunch of work when you're doing the limit as x goes to infinity. You want to be able to do most of this in your head. A little bit of work, but not a lot. We did more work with all of these than you're going to be doing from here on out. So let's take a look at 17. On 17, for example, what I notice, and it's in factored form even. So what does the highest power of x look like in the numerator if we were to multiply it out? We don't want to multiply it out. Let's just, what does it look like? So we've got the limit as x goes to infinity. And the highest power of x, that would be x squared times 4x to the first times 9x squared. Plus stuff over, and the bottom, if the highest power of x would be 32x to the fifth plus a bunch of stuff. Now, first off, is it bottom heavy or top heavy? What's the degree on the top? The degree on the top is x to the fifth. The degree on the bottom is x to the fifth. So it's not bottom heavy or top heavy. It's equally weighted. So we need the leading coefficients. Okay, so the leading coefficient for the denominator is 32. The leading coefficient for the numerator is 1 times the 4 times the 9, which is 36. So 36 over 32. Reduce it if it reduces. 4 goes into both of those evenly. So 9/8. That was pretty easy. Let's try this on 18. Okay, on 18, what's the degree in the numerator? The degree in the numerator, I've got x to the third times x to the first times x to the second. So isn't that x to the sixth? What's the degree in the denominator? I've got x to the second times x to the third times x to the first. That's also x to the sixth. Okay, so this one's going to be equally weighted. So we need to see what the highest power of x is looking like. So we've got the limit as x goes to infinity for, let's see, that would be negative 8x to the third times 5x times x squared plus a bunch of stuff over, down here in the bottom, I've got 9x squared times x cubed times 4x. So we already checked. It's already equally weighted. It's x to the 6th over x to the 6th. So up top we have negative 40. And in the bottom I've got positive 36. And if we reduce that, that's negative 10/9. Number 19. First off, let's check the degrees since it's in factored form anyway. So that would be x squared times x squared times x to the fifth. So that's x to the 9th on top. And on the bottom, I've got x to the 4th times x squared times x squared. That's x to the 8th. This one, we've got x to the 9th over x to the 8th. It's top heavy. The limit does not exist. Okay, so how much work do we actually need to show for these problems? Not very much. So because if it's in factored form, you might, this is the kind of work that probably would be good to show something like that. Maybe something like that on the last one. Let's take a look at a couple of the ones earlier and maybe see what kind of work we should have on a couple of them. So I'm going to go back to a couple of the ones there at the beginning. and put another piece of paper over it and take a look at that. Okay, so problem number 9. I look at it. Oh, it's equally weighted. Therefore, I just grab the leading coefficients. 3 over -2. And that was the answer. And that's the work I would show for that one. Let's take a look at number 10. Number 10, oh, it's equally weighted. So I would grab the leading coefficients. 2 over 7. And it doesn't reduce anymore. So that one's done. Wow, you mean it's that easy? Yes, it is that easy. Take a look at number 11. Oh, look, this one's equally weighted again. So I'm going to grab the leading coefficients. The leading coefficients are the coefficients of the highest power of x. So that would be 6 over -3. Oh, well, this one we're going to show a little bit of work, because 6 over -3, and then it reduces to -2.